All right, we are recording. So the first signal we're going to talk about is a delta function. And even though signals don't have to be functions of time, they can be functions of position or something else. Pretty much every signal in 110 will be a function of time. And in general, the shorthand is this kind of Greek delta symbol, right? And if t is less than 0, it equals 0. If t is greater than 0, equals 0. And if t equals 0, it equals infinity. Now, really, what that might look like is that you can have a shape, right? And let's have 0 here. And I'm just going to kind of draw the best I can a symmetric shape, right? And it's 0 here and 0 there, right? And let's just call the whole time that it's non-zero t, and we'll call this minus t divided by 2, and that point t divided by 2, right? And what can happen is that as, and we'll call that h, right? As t goes to 1 over infinity, right, h goes to infinity. And it doesn't really matter the shape and when you're doing this in practical terms. In fact, this kind of rectangle thing here could be a delta function. You know, this kind of shape could be a delta function. This kind of, well, let me try to draw that a little nicer. This kind of Gaussian shape could be a delta function, all right? The other definition is if I integrate that delta function, I'm going to get 1, all right? So whatever shape you use, as long as when you integrate over it, the non-zero part and get 1, that's a delta function, all right? Now, I think Wikipedia has kind of a nice plot animation showing this, and I'll just zoom in. Okay. And so this is the actual function that they happen to be using, right? And as we're letting a go to 0, right, we're getting this shape that is, the area is 1 and it's heading towards infinity as it shrinks. All right. Now, something that's 1 over infinity thin and infinity high, right? That's kind of hard to plot. All right. So how do we plot it? Well, we just draw a straight line up. Okay. We just put a little arrow on it at the head. And yeah, we just draw it 1 unit high, and we just know that that's a delta function, right? Centered at 0. All right, that's just, now, as we get into things, we can multiply these delta functions, right, by something. But what happens is, let's say I multiply this whole shape, right? Or I multiply this shape. But this has gone to infinity high and infinity 1 over infinity thin. Well, what good does multiplying do it? Infinity is infinity, right? Well, what happens is that if I multiply that delta function by a, the fact that the area is 1 and the fact that I've multiplied it by a doesn't come out until you integrate. All right. But sometimes what you can do is just kind of put like 2 times to recognize that that delta function is multiplied by 2. You wouldn't draw it. Well, actually, in some cases, you will kind of draw the height of that. And I think I found an example here where we've summed all these delta functions, and sometimes they're 0 or so small that they don't get plotted. Right here, these are the same height. These are all delta functions, and they're all going towards infinity or negative infinity, right? The only way you'll know is if when you integrate over these, the fact of what they were really scaled. So in a way, this plot it's not accurate, but it is a standard way of drawing things. Now, yeah, here it is with the arrows, and the code would need to be changed that if you had a negative value, it would be pointing, the arrow should point down. All right, so that's a lot right there. You know, we have this property of when we integrate it, we get 1 or scaled 1. It's infinitely high, it's infinitely thin. But when we draw it, we just draw the width of our pen with an arrow, right? And yeah, normally we keep it at 1, but again, you can scale it relative to whatever you've drawn it at. All right. So that was kind of a lot right there. What are your questions about that? And you can chat them. or put them in the chat.
Magic reverse, there's one thing I don't get.
Oh, hold on. Can you state your question? I had the wrong speaker on.
Okay, here's what I don't understand. Okay, basically as we've covered, these delta functions are infinitely high, but basically when we plot them, essentially some are actually scaled higher than the others. So that does that basically saying that some infinities are higher than others? That doesn't make sense to me. It's infinity, so by definition, nothing can be higher than it. So why are we scaling
Because I can't see who you are. Could you just say who you are?
Oh, it's Ray. Rayad.
Hi, Ray. Yeah, that drives me crazy too. And so, you know, when I was learning this kind of thing, or then when you go to teach it and you're trying to explain it, and then you see that there's some kind of major problem, like, you know, 1 times infinity and 2 times infinity, let's say from the mathematical world, should be the same, right? You can't plot it, but clearly, let's just run this again. And some people put dots instead of arrows, because you see when the dot is plotted upside, you know, going negative, you don't have to change the orientation, right? So I think, you know, I'm thinking you may have had a physics professor or a math professor who maybe beat you over the head with a stick every time you did a plot wrong, right? That didn't make mathematical sense, right? And the thing is in engineering, we kind of make approximations, or we're trying to visualize what's going on. So even though these lines are all to infinity, and these, now if they're 0, they're times 0, and then they just don't exist. But if I were to zoom in, these might be a little bit off the 0, but let's just take these, right? But they're plotted in relation to each other. And what that's telling you is that if I were to integrate over this delta function, I would get a positive area that's about half, you know, around half if I integrated over that delta function. And if I integrated over this, I'd get about the same magnitude, but it would be negative. Okay. And that what'll happen is as time goes on, this notation of scaling the picture, even though these all are supposed to go to infinity, it won't jar you. And what can happen is sometime you'll get so used to it, you might even forget that the delta functions go to infinity, and that these are infinitely thin. So Ray, did that help, or?
A little. At first, it sounds like kind of a
What would
contradiction
you like?
because
What would you like more?
let me make sure I got this right. Okay,
Right,
so one example of why this is important is because, like, for example, let's say we're plotting speeds. Like, for example, let's say 2 speeds are going to infinity, but let's say one might be traveling twice as fast as the other. So even though they can travel infinite distance, one is still going faster than the other.
could you slow down a smidgen?
Sorry.
So two somethings are going?
Sorry, sometimes I talk fast when I'm excited.
It's okay. It's okay. So do I.
Oh, so I think what you're trying to say is that even though they both go to infinity, they either cover different levels of area or possibly go at different paces. Like, for example, let's say we're plotting two essentially velocities that continue for an infinite amount of time. Even if they're traveling at the same speed, for example, one might still travel twice as fast as the other. So one covers more ground faster than the other.
Okay. So the first bit you said that these are representing areas, that these two areas are the same, and the area here would be half. That's right. Now, in this plot, these wouldn't represent, it's not used in the way you describe, in the example you describe, is that we're actually describing either a system or a signal. And in its own definition and world, and because this is discrete, that will be more your 112. So after, and if this was a continuous variable t, that's more 110. And what happens is that we really use that, the delta function, to kind of as a mathematical way to capture something, capture a value. So this isn't really today's bit, right? But let's say I had f of t equals sine 2 pi t, right? And I want to mathematically get I'm just going to call that a millisecond. I'm just going to sneak in the kilohertz there, right? And this is 0.25 milliseconds. And kind of, I want to capture that value, right? Mathematically speaking, I would do this integration. I would have my delta function, and then this is what I'm about to say is today's bit, t minus 0.25 milliseconds times sine 2 pi 1 kilohertz t dt. So what happens is I'm multiplying this, and when I delay this, that delta function only exists at 0.25 milliseconds rather than at 0, right? I delayed it. And again, we are right about to go over that right now. It's multiplied by the sine. So the thing is it only exists right at that time. And so what is sine, here, it's 1. So I get 1 times the delta function at that point. But if I was here, I delayed it here, I'm getting 0.5 times the delta function. And it would give me that value of whatever it is at that point, and it samples it. So as I shift that delta function to different moments in time, I am mathematically digitizing whatever happened in time. So I'm getting discrete time steps. But that might be a little bit much for today, but that is really how it's used, is that this is like the sampling thing. We were going to go more over this tomorrow. But the this here, you could just say, yeah, I was sampling some function at here, and here are the values that I got. Okay, that's another way to look at it. Does that help?
Actually, yeah, thanks.
Okay, I know it was effectively don't worry about it, but that really is how it's used. Anybody else with some good questions?
Hold on, it's up. Hold on. When there's a point here that says the right, Professor David, when it reaches a point, say Oh yes. When we're integrating infinity to negative infinity and e times delta plus t plus 7, which means, is there a impulse at that to t equals to negative 7 at that point? Like, is there like an activation signal?
Not quite sure if I follow you just yet.
Like something like this. Is it like something like you demonstrated here?
Oh, the big T. Oh, yeah. Anyway, sorry, that's the homework 1D. I'm about to go over the delaying. So maybe now's a good time that I'll do that. And what I'm also going to do is mute everybody because there might be some family members in the background. Not that I'm trying to get anybody not to talk. Okay. You can unmute yourself. All right. So I'm just going to keep going for the delay. All right. So more generically, I can have a delay term, or maybe call it better time offset. Okay. And what happens is if t is greater than 0,
Professor, I don't think you're sharing your screen.
oh, that's not good. I'm sorry about that. Okay. Yeah, 7 chats on that. So this is all that I wrote, is that you have a delta function and I'm adding a delay offset, right? Or time offset, because it could advance it or it could delay it. So if time is greater than 0, the signal will advance. And if the time is less than 0, it delays it. So, but what this kind of means is that if t is greater than 0, you're going to plot it on the negative axis, and if t is less than 0, you're going to put it on the positive part of the x-axis, because you've delayed it. All right. So so I'm just going to draw trying to draw some delta functions. Let me see the chat. Okay. Actually, I don't like that.
I can't see what the right text is.
I can go back to that. But I wanted to get more here.
I thought it was t minus t.
No.
Oh, it's plus?
T plus
Right.
t. And this is advances, sorry. Okay. So I'm just going to draw this over here. So it's drawn up to 0.75, right? And so this is going, this ft, this function of time, will equal 0.75 times the delta function delayed, it advanced by 1.5 seconds. Okay. And here, that's 1. This was 0.75, that's 1. And so that's really just the delta function. And then the time is advanced only by a second. Again, it's up by 1. So that's going to be scaled by 1. And it was delayed by a second. Okay. So that's pretty much it. You just draw it to scale, even though we know it's infinity. And if it's a positive, we know that that advances the signal in time. And yeah, so it's kind of a, an opposite type thing. If this is positive, it's in the negative region. If it's negative, it's in the positive region. But you're really just advancing and delaying a signal. Any questions on that before we move on to the step function?
I guess quick question, Professor.
Sure, shoot.
For the two that you did last, how come the last equation has the 0.25, but the first one doesn't have a times 2 at the end of it?
Could be my right, but this was delayed by 2, so that's minus 2.0, and this is only 0.25 high, and I forgot to write it first, so I'm having it here. This one was 1, so I just left it off. This is 1, so I never, this one was
Okay.
1, so I left it off. This was 0.7, so I put it there.
Mhm.
Yeah.
All right. Thank you.
Okay. Okay. Okay, so Juan, I'm sorry, I guess what happened was is someone wasn't able to hear that question. So what I'm going to do is repeat it. The question is why didn't this signal and this signal here have a 0.25 associated with it? And the reason is that I drew this 0.25 high. The reason why I put 0.25 after is I had forgotten to write it before. This is scale to 1, this is scale to 1, so I just don't draw the ones. And this one was scaled to 0.75, so I put it there. So that was the question. Not quite sure I was able to hear it, the question.
No, another student tried to ask a
Oh, somebody
follow-up.
else. Oh, well, whoever that, so if there's a missing question, why not just send me a chat?
Yes, sorry, I was using headphones that weren't really working with the mic. I was just
okay.
asking the timestamp that's associated with the delta being infinity at t equals 0. Is that the same time we're talking about when we're solving for these signal delays?
I guess if you come over to the definition,
Right.
right? So what it is, and this is, that's a good question. But I'm going to answer it a little bit over here, is that this gets substituted into T. So, and what happens is we just run out of variables, right?
Mhm.
So if I say, I define.
Right. So I
Yeah.
kind of
So if I define it here and then come up with another variable like tau plus 1 or T equals tau plus 1, then it just gets too difficult. And in a way, Python kind of takes this into account. So if I was trying to define a delta function, right? Now something wasn't quite working, so this is the wrong definition. So this code isn't working exactly the way I want. But if t is equal 0, return 1, else return 0, because we're plotting, right? It can't return infinity. And so if I want to, so here's where I call the function, right? But if I do t minus 1, it substitutes this whole t minus 1 right into here. So it's a very Pythonic way of looking at it. But yeah, thanks for asking that, because that is something that I get used to, and I forget that it's like actually you have a function, and I think it's time to move on to the next bit, is that if I have a function, right, whatever I want just gets substituted into this function of t. Okay.
Okay. Thank you.
Yeah, no, thanks for asking that. And thanks, Juan, for pointing that out. All right. So the next function we're going to do is a step function. And the shorthand is UT, because really it's the unit step function. Because essentially it goes up to 1. All right. And it equals 0 when t is less than 0. And it equals 1 when t is greater than or equal to 0. Okay. And we can scale this right? We can multiply it by a constant. And so if a is 10, this will be 10 when t is greater than 0, and it'll still be 0. But we can also advance it and delay it. So I'm just arranging things here so I can try to make a little more coherent plot. So that's UT. Now, yeah, this goes on for infinity, and it's 1 for positive infinity and 0 for negative infinity, right? It never. Now, what you'll find that step functions, right, are actually things that you can start to approximate on a function generator. You can do that for delta functions too, but you always have to kind of scale things to get the areas right. All right. And yeah, mathematically, we have an infinite slope here. And in fact, if we integrate rather than integrating from negative to positive infinity of a delta function, but if we go from negative infinity and then the upper limit of integration is t, we get the step function, right? So that's next time, all right? So let's do another one. So it's scaled by 0.25. It's a step function. And it was advanced by 1. We're scaled in this case by 0.75. It's a step function. And it is delayed by 1. Now, and in this case, we'll still call that a step function. it's delayed by 0.5, but it's scaled by minus 0.75, right? And so, yeah, delta functions can be positive or negative, and step functions can be positive or negative as well, all right? So now, what I'd like to do is plot, a composite function. So let's UT plus 1. Will the step be on the negative side or the positive side?
Negative side.
Yep. And it's going in the positive direction. Goes up to 1. And it goes on forever. Likewise, where's the discontinuity on this one, the positive side or the negative side?
Positive.
Positive, right. Okay. Well, now to find the composite, we just add them. So 0 plus 0 is 0. 1 plus 0 is 1. 1 minus 1 is 0. And that just continues. I'm not going to change colors each time for this one. So we have 0.25 with an advance of 2 seconds. So all I got to do is just draw a little bit, come up to 0.25. And draw across. And then I have another signal. It's advanced to 1.5. It comes up to 0.25 and continues. And we have the same signal delayed again. Oops. Not as necessarily as drawn as nicely. And then we have okay. So those are all the individual signals. And I'll take purple. So we're coming along, 0 plus 0 is 0, and we add 0.25 and we go to 0.25. We add another 0.25, we get to 0.5. Add another, and then we add it all the way up to 1. So we've staircased it, and then nothing happens until 1 second when it all cancels out.
Professor, it should be 2 seconds, right?
Did I say 2? I said 2. Thanks. Okay. Now, we need to get to ramps, okay? But what an exam question would look like is, here's a function that I plotted. You tell me what it is, right? And yeah, I know something is going to happen here. So that's something I need to, it flattens out here. I have a change. And I have a change. So 1, 2, 3, 4. So the thing is you might not get the ramp yet, right? But you can tell based on what I've done so far that your equation should have 1, 2, 3, 4 subfunctions with different times. Now, sometimes the times you can have more than one function happening at the same time, okay? Which is, in this case, you're adding a step to a negative ramp, but So here's the basic ramp function, just RT, and we can scale and delay it as well. All right. And normally it would just be T, but when we multiply it by UT, we actually get the ramp function. So what do I mean by that? That's T, right? For negative time, positive time, there's always a slope of 1, right? But UT is 0 before that, right? I mean, RT equals time. Well, we have the time times UT. So let's just redraw UT again. So when I multiply these together, well, 0 times anything is 0, and then 1 times the thing is the thing. So ramp T, actually before we switch to that, so that's UT. Okay, it goes on forever, right? And never comes back down. Now, how does this play out? Let's do a composite functions, okay? So let's start off with a ramp. Then I'm going to subtract a ramp at 1 second. So let's draw a ramp. Right? And I'm just going to try to put an arrow there that it's going on forever. Now, what about the subtracted and delayed ramp? So I'm at 1, but now I'm going down. All right, let's add them together. 0 plus 0, a slope of 1 plus 0 is 1. I mean, a slope of 1. But now the slopes are being canceled out. And so it flattens out. So I have 1, 2, 3 times. So I should have something changing direction at 2 different times, at 3 different times. So let's do the RT first. Now minus 2RT. So we did before, we did minus a delayed RT, right? And before we did a slope of 1. Now I'm just going to try to draw a let me just try to draw the slopes. Okay. Zero plus 0 is 0. A slope of 1 plus 0 is a slope of 1. A slope of plus 1 minus a slope of 2 will give me a net slope of minus 1. And then when I take a net slope of minus 1 and add a slope of plus 1, it flattens out. And so with ramps, so when plotting ramps, notice how I'm not, where does it start? But I'm keeping track of the net slopes, right? With keep track of the net heights.
Professor, I have a question.
Yeah.
Does that just mean that square and triangle functions are just composites of ramp and step functions?
I'm sorry, somebody was hammering in the house. So that's a rectangle, right? Yep. That's a composite of a steps, right? And you might even, now is a ramp a composite of a T and a step? You know, okay. But definitely the triangle is a composite of ramps. So yeah, that's definitely true. That was your question, right?
Yes, thank you.
Okay, good questions. So I know we only have about 5 minutes left, but this would have been like an exam question from years past, right? So what was this function? All right, and I'm just gonna scroll over here. And I see something changing here, something changing here in time, and something changing here in time. So my function should have 3 times, but that doesn't mean that I only have 3 functions, okay? Because notice things that we've done so far, right, are kind of a step and ramp, right? And we've done ramp down, and yeah, we've done step down. And so we have something that steps, right? But then right away, we have something that's ramping. So in fact, and I'm just going to put that that's 1.75.5. Okay. So in fact, f of t, yeah, I step up. I have a step of 1. But something else is going on at t. Is that now I have a negative slope. Well, that's how I would get it. That's that discontinuity. Now, if I did nothing else, right, this would actually keep going forever. So something's got to happen here at 1. Now, because I have a net slope of 1 up and it's not discontinuous, it's got to be a ramp. So I'm going to have some kind of positive ramp. Now, before these were happening at 0. Now this is happening at 1. So I've delayed it by 1. Now, if I'm going down 1 and then I'm going up 1, that was like a change of 2, right? So I have to do the 2 there. And then here something happens. I go down by 1. All right, so that's easy. A big discontinuity like that, and it happens at -2. But if that's all that I did, you know, I go up, I come down. I mean, I go up and start coming down at the same time, right? Then I change direction. Okay. So now what happens is if I only go down, it'll keep going, right? So not only do I have to go down, right, I have a slope of going 1, and now I have a slope of 0. So that means that flattened it out. So in this case, yeah, I had to keep track of heights. And at 0, I had 2 things happening at the same time. Then right here at 1, I only had 1 thing happening. But then at 2, I had 2 things happening. I changed the slope and I was discontinuous. And so what I have are, for the midterm, question 1, I have an algorithm that will generate unique plots for everybody so that you all have something unique to do. All right. I know we're running a little bit out of time, but I wanted to talk about, so there's something that I have here, a link, student success in 110. All right. Now, yeah, I'm probably going to delete this because this was the circuit stuff, right? So that's actually in the review here. Okay. But these exams are open book, open note. And what you kind of want to be doing now is creating your study guide or your so-called cheat sheet, so that when it comes time for the exam, you're not trying to like hunt up for information. Also, when you do your own thing, I find that even by writing this, like I'm learning it even better myself. Although, truth be told, maybe you'd rather do it in pen and paper. But here's midterm 1, right? Sample question 1, describe a signal. What would I put in a cheat sheet? I'd have a definition of step, delta, ramp, and delay and scale. I might even have some Python code to write to check my answers, or Desmos, right? And that way I have it all right there. And making the study guide will also help study. And then the next thing is so this homework is due due on the 7th, right? When you do the next homework here on the 15th, right, it's been a whole week since you've done that kind of assignment. And so you want to go back and kind of just do a refresher, all right, so that it's sticking in your mind, all right? That's just some advice I have, you know. Any questions before we go?
Professor,
Yes, sir.
what would RT minus mu t look like? I know you closed the thing, but
Listen, if you got to go to 112, go. I'm still recording, so I can still answer this question. So what was your question?
RT minus mu t.
This?
Yeah.
Okay. Now, yeah, you know, I apologize. Sometimes I write it as like that because of my device physics background, but I'm really trying to draw lowercase u. Well, let's do it. So RT. Okay. And it's coming up, right? Goes on forever. Then we have at the same time minus UT. And it goes on forever. Let's sum them up. So make it bigger. 0, 0 plus 0 plus 0. Now I've subtracted 1 from 0, but then it's rising, and it keeps rising forever and ever, unless I flatten it out. Okay? So to flatten it out, I would have to subtract. I mean, the way I drew, I think I drew the slope. I didn't draw it quite right. The slope was off. So in fact, I drew 1.5 RT, but I think you get the picture. Okay. All right, everybody. Have a good evening.
Professor, I have a quick question.
Sure.
Will these notes that you just drew be uploaded or just the
Not really, because it's in smooth draw, and then they're pretty ugly.
Okay. Well, I'll
I do
just,
the record. I'm gonna post the recording.
yeah, I
Okay.
think that's good enough. Thank you, Professor.
Yeah. Now, yeah, just so you know, I am trying to do some notes here with maybe, like in 98, I might say, oh, here's a figure. And then I link to some Python. I guess I haven't linked to the Python code yet. So I'm trying to come up with some better notes. But yeah, no, I'm not. Now, those I don't want to really publish because they're ugly. Okay. All right, everybody, take care. Remember, office hours are from 9:30 to 10:30.